Hi everyone, welcome to my talk on distilling GHZ states using stabilizer codes. I'm Narayanan Rengaswamy, a postdoc at the University of Arizona with Bane Vasic. This is joint work with Ankur, Raina, Nithin, Raveendran, and Bane Vasic. You can find the full version of our paper on arXiv and our implementation on GitHub. We would like to thank the organizers for selecting our work as a lightning talk, and we would like to thank the reviewers for providing helpful feedback, and we'll address some of their comments here. Entanglement distillation is an important subroutine in quantum networks. It refers to starting with a noisy entangled state and producing many copies of higher fidelity entangled states as output. Now, the standard setting is to consider n noisy copies of the bell pair as the input and to perform some operations and produce k output copies of the bell pair of higher fidelity as the output. Now, many protocols in the literature are 2 to 1. They start with 2 noisy copies of the bell pair shared between Alice and Bob, and they perform bilateral operations on these qubits and later measure one pair. And if the measurements agree on Alice and Bob, then the other copy is a perfect bell pair. But asymptotically, these protocols are inefficient because they tend to consume many noisy copies of the bell pair to produce one higher fidelity output bell pair. The connection between entanglement distillation and quantum error correction was introduced by Bane et al. In 1996, where they showed that one can convert any quantum error correcting code to an entanglement distillation protocol that uses local operations and one-way classical communication. Later, Wilde, Crovey, and Brun considered this slight variation of that protocol to distill bell pairs. Here, Alice starts with n copies of the bell pair, sends 1 qubit of each copy to Bob over a noisy channel. And so effectively, this creates n noisy copies of the bell pair shared between Alice and Bob. Then Alice picks some stabilizer code and measures the stabilizers of that code, and later perform some recovery operation to fix the syndrome. This effectively projects her qubits onto the subspace of that code, and she sends the stabilizers and the syndrome through a noiseless classical communication channel to Bob. Now, Bob uses the transpose property of bell states to figure out the effective code on his qubits, and he measures the stabilizers of that code to correct for errors in the channel. And if error correction was successful, then the logical qubits here are logical bell pairs, which are converted to physical bell pairs by inverting the encoding unitary or performing the decoding step. So this is the overall protocol. We explain this protocol and the subtleties of this protocol using the stabilizer formalism of Gottesman, and later extend the protocol to GHZ states. When we distill the GHZ states, it is better to directly distill them rather than first distill bell pairs and then fuse them, as shown in this paper by Moral et al. Now, our work enables high rate, high output fidelity entanglement distillation using these recently discovered quantum low density parity check codes, or LDPC codes of high rate and high minimum distance. The LDPC property is very useful because it bounds the weight of stabilizers that you have to measure. This is how our protocol works. Alice initially creates n GHZ states and measures the stabilizers of some code. Then we show as our main technical result that this induces a 2n qubit code on all the remaining qubits. So she sends all the remaining qubits to Bob, who measures this 2n qubit stabilizers to fix the errors in the channel. Later, he also measures the same stabilizers as Alice, but just on his qubits. And the purpose of this is to induce a code on Charlie. To make sure that Charlie's code is the same as Alice and Bob and non-trivial, Bob also performs a Clifford operation, a diagonal Clifford operation on Charlie's qubits. And this is crucial. And finally, all of them invert the encoding unitary as in the Bell protocol to convert the logical GHZ states into physical GHZ states. Now, with some thought, one can show that this Clifford operation can be done either by Alice or Bob, but who does it has a big effect on performance. And we also consider variations of this protocol in the paper. Now, let's consider the standard 5 qubit code on the standard depolarizing channel. So the standard quantum error correction, no distillation. This produces the spin curve, which has an exponent of 2, which basically means the curve scales as epsilon squared, where epsilon is the depolarizing probability. Now, if you come to this protocol, if no Clifford is done, or if Alice does the Clifford, you get these top curves, which has an exponent of 1. Whereas if Bob does the Clifford, the exponent improves from 1 to 1.74, which is closer to 2. So going forward for larger codes, it is always better for Bob to perform the Clifford operation. In future work, we'll consider more variations of this protocol that are more practically relevant. We'll also consider local noisy operations and investigate the effect on the protocol. And in this work, we also give a new algorithm to distill to produce logical poly operators for any stabilizer code. Thank you for listening.